everyone. So in this video, we're gonna go over chapter 6, simple linear regression. Now, regression is a very important topic in statistics, economic forecasting, or anywhere when you need to analyze data. Now, in this chapter, we're gonna talk about the simple linear regression. And in the next chapter, we're gonna talk about the multiple linear regression, okay? So some basic ideas. The basic idea of a regression is to use a mathematical model to represent the relationship between two variables. We call one variable the dependent variable, labeled as y, and the other called independent variable, labeled as x. And of course, as you can tell, we would expect that the dependent variable y depends on the independent variable x. When we only consider one x, we call that the simple linear regression. And when we consider multiple x's, then we say that's the multiple linear regression. But the idea and basics are the same, whether we are looking at simple linear regression or multiple linear regression. Okay? And we use regression really to represent what we observe in the real world, and we want to have it simplified. Because when you look at data, right, they are numbers, and you want to use a simple way to describe how one variable is changing with the other. You might say, well, we've learned correlation coefficient. That tells me whether x and y are highly correlated or not so much correlated. That is true. But with regression, we want to also find out how y will change when x changes. Okay, not just the direction of the relationship, but also by how much. If you want answers to those questions, then you need to look at the simple linear regression or multiple linear regression. So here are just a couple of examples where you will find regression analysis being useful. So the first one is related to the housing market. When we have housing starts changes, of course, the demand for building materials will change. And for the suppliers or the retailers of building materials, they would like to know how housing start changes so that they can predict the building materials they will be able to sell, right? And so we would expect housing starts be related to building materials. In addition, we also want to know if housing starts, let's say, for example, increase by 10%, what happens to the sales of building materials, or what happens to the demand of the building materials. Now, similarly, as you can imagine, the number of babies will also influence the baby product sales. Not only we know that when the number of babies increases, the baby product sales will increase, we sometimes also want to have a more concrete number and tell us when the number of babies increase by 20 or 100, what happens to the sales of baby products. There are more examples for your reference. You can look at these yourself, and they should all make sense for you. Next, let's talk about the simple linear regression model. And let's say it's a model because it just generalizes the basic relationship between x and y for any data set we may consider. In the model, we have the dependent variable y and the independent variable x, and we assume they follow a straight line relationship in the following format. So we will say y is equal to beta 0, that's a parameter, plus beta 1, another parameter, times x, plus an epsilon, and that's called the error term. Let me provides more details about these parameters as well as epsilon. The beta 0, okay, and that is called the y-intercept. Some people may call this a shift parameter because the beta 0 will determine where your line starts from along the y-axis, right? Where your line intercept with the y-axis. Of course, the higher beta 0, the higher the line will intercept with the y-intercept, with the y-axis. And beta 1 is called the slope coefficient. It's basically the slope of the line, and it indicates whether the line is steep or it is flat. It also tells us how y will change as x changes. And this is really the additional information that we can get from regression, other than just looking at the correlation coefficient. Now the last term, the epsilon, which is called the error term. Now the error term is actually something we've talked about before. It is basically the difference between the actual data and the estimated value or the forecast from using the model. So it's basically the residual we've been talking about for quite a while. Okay, the error is always not the mistake, but this difference between what we actually observe and what we can predict or estimate using the model we decided to pick, okay? So that's the model that will be applied to data. Now, in terms of regression forecasting or regression analysis, we have a couple of steps. In the first step, we want to specify the model, okay? We only talk about the simple linear regression model so far, so that's one. There are cases where we may want to transform the data before applying the simple linear regression model. And there are a lot of situations where we want to use multiple linear regression model instead. Once we decide the model, we can fit the model to the data, and we call that step the estimation. The estimation basic just means within the model, we want to identify beta 0 and beta 1, replace them with specific numbers. And in the third step, it's the validation step, which means we want to verify whether our model is valid or not or adequate or not. Okay, we can't just assume whatever model we fit to the data, it would work. So we need to verify that. And lastly, once we can confirm our model is valid, is doing a good job, then we can do the forecast. So we're gonna follow these steps. Therefore, the second step is the estimation. We've already talked about the model, and so far we only have the simple linear regression model. Now the second step, we estimate the model. So from the original model, if we can use the sample data to verify beta 0 and beta 1, then we will rewrite the estimated regression as the following. And notice that this time there's a little hat above y because we are using the data. Okay, so now hopefully you will realize whenever there's a little hat above something, that means data is involved. We used data to do the estimation. So this estimated y is equal to b0 plus b1. And of course, b0 and b1 are specific numbers. Once we use the data set, we are able to replace b0 and b1 with actual numbers. X is still the independent variable. Now you may ask, where does the error term go? Well, the error term actually, once we use the data, to a certain term disappear because the error term will capture the difference between the actual y and the estimated y. And therefore, you don't see the error term within the estimated regression line. And the method we're gonna use to estimate the simple linear regression model is called least squares principle or least squares method. in this method, what we are trying to do is basically trying to minimize the forecast error, or trying to minimize the difference between the actual data and the estimated value. But you would see two terms, least, that makes sense because we're trying to minimize the forecasting error. But why squares, right? Why we need to square something? It turns out what we are trying to minimize is not just simply the forecast error, okay? It is actually the total of the squared errors, which means we obtain the error first, square them, and then add the squares up. And there's reason behind it. Basically because sometimes the actual y is higher than the estimated y. Sometimes the actual y is lower than the estimated y. And therefore, the error term will be positive and negative. So you can't simply add the error terms up because the positive ones and negative ones will cancel each other out. And therefore, you want to square them to make all the errors to be positive, then add up the squares. Okay, so next, let's look at an example and see how we use the least squares method to do the estimation. Suppose Mr. Bump observed the selling price and sales volume of milk gallons for 10 randomly selected weeks. Mr. Bump is interested in estimating a simple linear regression model to investigate the relationship between price and sales. Okay, on the left-hand side, you see the table with the data, and there are 3 columns. We have the number of weeks, 10 of them, and then we have the sales, which is denoted by Y, because the sales depends on the selling price, and we all know that. That's common knowledge, right? And as we would expect, the higher the price, the lower the sales. And therefore, if you look at the scatter plot on the right-hand side, it does show that we can observe a kind of downward sloping trend, right? So basically, it tells us sales and selling price are negatively related. So here's a little bit more details about the least squares method in terms of this specific example. The overall goal is really to minimize the difference between the actual y, which are represented by these little dots, and the estimated y, which are represented by the values along the line, okay? And in particular, we're looking at the vertical distance between each observation and the line with it. We want to have all the vertical distance minimized, and you would recognize that the vertical distance is actually just our forecasting error, okay? And the best line will be the one that can make all the vertical distance minimized. The good thing is, least squares method, sometimes we call it OLS, will enable to do that. The actual method does involve calculus, derivative, things like that, but we will skip all those discussions altogether and move to Minitab. So I want to show you how we're gonna run the regression Minitab and come back to the results, because we're gonna go through the results in much more details. So here we go. The name of the file is Mr. Bump. We see 3 columns, and we are interested in particular the weekly sales and the selling price. So let's do the regression analysis. We're gonna go to stat. This time we go to regression. Regression again, and we want to pick fit regression model. So click on it. Now the response variable in Minitab is basically the Y variable. So we're gonna pick weekly sales. And you will see 2 boxes for the predictors. The predictors are basically the X variable, or the variable we used to predict. Now the response variable is the one we want to predict. there's continuous predictors and there's categorical predictors. So far, we will only be using continuous predictors, which is the selling price for this example. Now, later on, when we deal with categorical variables, meaning for the data, we are looking at categories, then we will come to this box and pick the categorical variables. Before then, we always put our X variables within this box. Nothing needs to be changed as of right now. We might need to do extra steps later on, but let's click on OK and see what we've got. Okay, so for regression analysis, you don't see graphs anymore. You see tables. And basically, all of these tables are important ones. We will be looking at almost all of them. Maybe for simple linear regression model, we will not go to the last one, analysis of variance. But for the first three, we will definitely visit them. So let's go back to the PowerPoint slides and continue our discussion. And here we are. On the right-hand side, you see the same output as we saw in Minitab, and I circled all the numbers that are important for us in terms of this output. On the top, you see the regression equation, and then the next table is the coefficients. They are the estimate for beta 0 and beta 1. And in the next table, we see the model summary. So we're gonna go through everything one at a time. Number one, the estimated regression line. It is given as 32.14 minus 14.54x, okay? And there are several things we can tell from this just one equation. Actually, there's a lot of information. The first thing we know is that now we can specify B0, which is the y-intercept, to be 32.14. And we also know that B1 is specified to be negative 14.54 for this particular data set. In terms of B1, which is the slope coefficient, it tells us at least we see x and y are negatively related because the slope is negative, and that is expected. The other thing we can say just by looking at this number is that now we can tell if the selling price changes by a certain amount, what exactly will happen to the sales, okay? And that is the interpretation for our slope coefficient. And this is how we usually interpret the slope coefficient. We say for every dollar increase in the selling price, which is X, the weekly sales will decrease on average by 14.5 times 1,000 gallons because the data are in thousands of gallons, which is basically 14,540 gallons, okay? That's one way to interpret the slope coefficient. Usually, we wouldn't change the selling price of milk by $1, right? So it probably will make more sense to say for every cent, right? For every cent increase in the selling price, the weekly sales will decrease on average by 145 gallons. That will probably give people better idea. And it does matters, right? For even 1 cent, you change your milk price, you will see 100-gallon decrease. And this is also reflect the competition in the milk market. Now back to B0. We didn't interpret that number, 32.14. It turns out we can't make sense out of it. So we usually say that B0, the y-intercept is meaningless. Why? Because basically the y-intercept just tells us the value of y when x takes a value of 0, right? So when x is equal to 0, X equal to 0. What about the Y? But we need to ask, would the milk price, the selling price of milk, be 0? It won't, right? Nobody will sell milk free. So you won't ever get there. And therefore, it can't make sense to interpret this and say, well, if the selling price is 0, right, you're going to sell 32,000 gallons. No, if the price is 0, you can definitely sell more than 32,000. I don't know how much, but it definitely won't be a small number. Okay, so that's the first estimation, and we were able to interpret the slope coefficient, which is the key number we find. Step 3, validation. I know we haven't go through every numbers in the output, but some of them is for the further steps. So step 3 is validation. And for validation, we want to look at a couple of things. Number 1, we want to look at the sign of the slope coefficient. Does it make sense? If we expect to be positive, do we see positive in the slope coefficient? We also want to conduct a t-test of the slope coefficient to make sure that yes, X and Y are indeed significantly correlated. And then the second is we want to look at the f-test, but we're going to reserve this for the multiple linear regression, because basically for simple linear regression, since there's only one X, it is sufficient by just looking at the t-test. So we will skip this in this chapter. The third item that we're going to look at is called coefficient of determination, or a lot of times people call it R squared. And this item will tell us how well our model fits the data. Is it a good fit? Does our model represent the data very well? Apparently, in the previous chapters, when we look at trend analysis within decomposition, we recognize that when there is strong seasonality, that linear trend cannot represent data that well. So here in regression analysis, we carry the same logic and ask, can our model represent the data well enough? And lastly, we're gonna check the least squares assumptions. And to check that, we'll be looking at the residuals. So let's go through the first one, t-test of the slope coefficient. And basically, with this test, what we're asking is, although you see a slope coefficient estimated in the regression line, does it indeed mean that X and Y are significantly correlated in the whole population? Because after all, the slope coefficient we've got only represent or is derived from that particular data set. We don't know for the whole population whether this relationship holds or not. And the beauty about this t-test is that it will allow us to generalize what we observe in the data to the whole population. It will allow us to determine for the whole population or for all milk sales, whether sales and price are significantly correlated as we've observed in the data. Okay, so in terms of t-test, we are testing on beta 1, the slope coefficient, because if the slope coefficient is 0, that is if beta 1 is 0 in the model, then basically X will be dropped from the model and Y is not related to X. And that is something we never want to see. It happens sometimes, not that often, but it is something that we don't desire. So the null hypothesis means there's no linear relationship, which basically means, well, you shouldn't have estimated a simple linear regression in the first place. Now, the alternative states that the slope coefficient is different from 0, and we like that. As long as the slope coefficient is different from 0, then we can say there's a linear relationship between the two variables, all right? And notice that this beta 0 is not equal to negative 14.54. Negative 14.54 is the B1. B1 is an estimate of beta 1 based on the data. Beta 1 represents the overall relationship between X and Y for the whole population for all milk sales. Let's look at this part of the output. All right, we haven't looked in more details, although we specify the regression equation. But in terms of these two numbers, B0 and B1, they are listed in this table as well, and they're called coefficient. You notice that the coefficient for constant, which is y-intercept, is 32.14, and the coefficient for the selling price, which is x, is negative 14.4. To perform the t-test, we will go directly to the p-value, which is circled right down here, okay? So that's the p-value for the t-test. And remember, for hypothesis test, we usually rely on the p-value, and the criteria is the following. If p-value is, I'll just say it this way, greater than 0.05, and by the way, 0.05 is the significance level we usually use, then we do not reject the null hypothesis, or H0. I'm going to put H0 there and put a note that's the null hypothesis, okay? If p-value is greater than 0.05. If p-value is less than 0.05, reject the null hypothesis, which is H0. And I'm gonna say, this is the one we usually like. This description is not very accurate. Actually, it's not rigorous, but I do believe it will help you to better remember what we like, the result. So this is what we desire a lot of the time, but whether we'll get it or not, we don't know. It depends on the data. So that's the p-value approach or p-value criteria. You would notice that the p-value for this case is 0.001, which is less than 0.05. So that's good news. We can reject the null hypothesis. So we can declare that this statement, no linear relationship, is wrong. And we can conclude with the alternative and say, yes, X and Y are significantly correlated. Or going back to the specific variables, we can say the sales and price are significantly correlated. That's the t-test. Next, let's look at R-squared, which is the measurement of fitness of the model. Or in other words, how well our model fits the data, okay? So I need to go through a thinking process before I can tell you how we judge the fitness of the model using R-squared. Let's think of the regression analysis as a process of trying to explain the variation in Y. So basically the question is why we observe different sales of milk. And I'm sure you can come up with a lot of reasons, okay? One thing could definitely be the price. If the price decreases, more people tend to buy more. If the price increases, people may wait to buy later. Price is a factor. What else? Well, if we're talking about a particular brand of milk, then that also depends on people's preference. How many people like to buy that brand? In addition, the prices of other brand can also affect the sales of this particular brand because they are competitors. If the competitors lower their price, you will not be able to sell more. If the competitors increase their price, but you are offering discount, you will be able to sell more. But in our model, what we included is just the price. We didn't include other factors like people preference or competitors' price. So we're gonna separate the variation in the sales into two chunks, okay? And let's first denote the total variation in sales as SST, okay? And the total variation in terms of numbers is 233.6. That's SST. And in case you wonder, SST stands for sum of squares total. Don't worry too much about the terms. What you need to know is this is total variation in sales. We separate into two chunks. One part is we call SSR. That is the variation due to price of the milk. When price of the particular milk increase or decrease, you will see sales change with it. And we will say that's the amount of variation associated with the price of the milk. In terms of numbers, it's 174.19. As we just discussed, there are other factors that can affect the sales as well, and therefore they can cause the sales to change. That part of the variation is denoted by SSE, is the second chunk. And in terms of numbers, that's 59.41. And these are due to all other factors that are not included in our model. Basically, just all other factors other than the price of the milk itself. Since we are taking price as the variable to include in our model, then it must mean that we believe price is the most important factor among all other factors, so that we decide to take this one out and use it in our regression. And therefore, if we believe price is the most important factor, then we would expect price to explain most of the variation in sales. Okay, or in other words, we would expect price to cause most of the variation we observe in sales. We would answer the question as, you know what, sales increases or decreases just because the price of the milk changes. And that's the most important thing. And therefore, in terms of our model, the more variation in sales that can be explained by price, the better our model will fit the data, because we got the right variable. We got the right model to explain the variation in sales. The R-square is exactly measuring the percentage of variation in sales that can be explained by the price or the model. As we mentioned, the more we can explain using price, the better the model fits the data. And therefore, as you can imagine, in terms of this R-squared, of course, we want it to be as high as possible. What is the highest? 100%. That means all variation in sales is just due to price. Is it realistic? The answer is no. That never happens. If it happens, if price is the only factor that affects the sales, then you don't need statistics. You don't need anything we discussed here. Just go ahead, set your price, you will know your sales. And just because there are other factors affecting sales, then we need to learn the regression model. You might say, wait a minute, why don't you include other variables so that we can predict the sales perfectly? Unfortunately, the answer is still no. You can try to include other variables, as many as you can, the price of other brand, people's preference, even weather, but there will still be this random measure, randomness. What if one day I go inside Kroger and decided to buy 2 gallons of milk instead of 1 gallon? Out of no reason. That's the randomness, and you can't predict behaviors like that. So there will always be something that you can't explain using the model. But again, the purpose of using the model is to try to explain most the variation in sales. So the idea for R-square is the higher R-square is, the better the model fits the data. So we want high R-square. But the highest one will be 1. That's represent 100%. And there's another typo here, I apologize. The range should be from 0 to 1. I will fix this in the PowerPoint slides shortly. R squared cannot be negative, right? In terms of our particular example, you will find R squared to be given right down here in the model summary. And that percentage is 74.56. Is it a high percentage? Not really. Is it bad? Not either. So in terms of how high R squared should be, there's no criteria. It really depends on it's really a case-by-case situation. It also depends on a person's opinion. And for this particular example, 74% is not high. We can definitely do better than that. In particular, we know for the sales of milk, there's other factors can affect it than just price. Okay? So next, the criteria we're gonna look at is the model assumptions. We can fit the model to the data, but we actually assumed a lot when we're doing that. So here are the assumptions. Number 1, normality. We want the dependent variable y to be normally distributed. Number 2, we want constant variation. And we have a specific term for that. It's called homoscedasticity. Okay, it's a long word. It just means constant variation. That is, we want the population variance to be constant. If this condition is violated, that is called heteroscedasticity. Number 3, we want x and y to be linearly related. Of course, you may say, that's why we're fitting a straight line relationship. You bet. There are situations where this assumption is violated. And actually, we saw that in the previous chapter already. For some data, it's not appropriate to just fit a straight line, right? A curve is much better. And lastly, we have these following assumptions for the residuals. Just because we want y to be normally distributed, we want the residuals to be normally distributed. We want also the residuals to be random, meaning that, similar to what we learned before, after we use the model to capture the data, we want the model to capture anything that we can predict, anything that is systematic. So whatever left is just the randomness. We also want the residuals to have constant variance, and this is also related to number 2. We want the population variance to be constant. Sounds a lot, right? We have so many assumptions. Don't worry too much, because once we examine the residue, we will be able to check on every one of them. So what I'm showing here is the residual plot for the simple linear regression model from Minitab. And right now, let's head over to Minitab and see how we can obtain all the graphs on there. All right, so here's the Minitab, and we want to obtain the residual graphs. Therefore, we have to re-estimate the model. So we're gonna go to Stat, Time Series, regression this time. I use time series too often. And then regression again, then take fit regression model. Among so many options, you will see graphs. So click on it, and we want the residual plots. You can pick individual ones, or actually most of the time, I just say I want all of them to be one picture. So click on OK, and OK again. This time, the graph will show up. So these are the residual plots for our regression analysis. And we can use these graphs to check if the assumptions are satisfied or not. So returning back to PowerPoint slides, here we go. Let's examine all 4 graphs and see what conditions can we check using which graph, okay? Number 1, assumption of the residuals. We want it to be normally distributed. And when we check on this, we are checking on Y at the same time because the residue represent Y after taking away any systematic pattern. And we have 2 items for checking the normality actually. The first graph, which is normal probability plot, and also down here, the histogram, okay? In terms of the normal probability plot, what we want is to have all the dots represented by the blue ones to be following along a straight line. Or in other words, the closer they are to the red line, the better. In terms of the histogram, we want it to be roughly this bell-shaped. Now, when you look at these 2, you don't want to be too strict with it. For the first one, to me, that's roughly a good line. Okay, I'm gonna say the blue dots are close enough to the red line. And I'm gonna say the normal distribution assumption is not violated. Down here for the histogram, although it's not a very neat bell curve, I still see a peak in the middle, and then to both sides it's going down. So I'm gonna let it go and say, yes, the assumption is satisfied. For second, residuals needs to have constant variance at the same time while also checking whether the variance for the population is constant or not. What we do is to look at this graph down here is the residue versus fit, or in other words, it's the residue versus Y hat. And what we are looking for is the distribution of the blue dots or the scatteredness of the blue dots. Are they constantly scattered along the line in the middle? To me, they are. And I want to show you a situation where the variance is not constant. So back to on this page, if you look at this scatter plot, it is still the residual versus the fitted Y. You would notice that the dots are fan-shaped, right? At the beginning, the variance is small, but towards the end, the variance is big. In this situation, we say we have heteroscedasticity, and we say the assumption of constant variance is violated. Then we need to do something to fix it. Back to our case there, I don't observe anything like that, so we are good. Now for the third item, we want to check to see if the residuals are random or not. Plot the residue over time, as what we have here, and we want it to be purely random. We don't observe anything systematic, okay? What if we observe the residuals going up and down in a very neat pattern? There we're gonna say, you know what, something is wrong. The residuals are not random, and apparently there's some systematic patterns that the model didn't capture. So overall, for our example here, all assumptions are satisfied, and we're gonna claim the model is valid. We will not say the model is a very good fit based on the R-square, but we will say the model provides a reasonable fit to the data. So that's the analysis of the residual. So finally, if we determine the model is valid and we determine the model provides a reasonable fit, we can start a forecast. We actually did this before. When we do forecasting, what we do is really replace X with the corresponding value and go through the calculation to find Y hat. So here's a particular example. It says, suppose Mr. Bump wished to forecast the quantity of milk sold if the price was set at $1.63. Then we just plug into the regression equation, go through the calculation, replace x with 1.63, then we'll find out the quantity of milk sold will be 8,440 gallons. The question is, if this happens in the real world and Mr. Bump really set the price at $1.63, should he expect his sales to be exactly 8,440 gallons? Of course, the answer is no. You know that, right? Our prediction is just providing a reference point. You can't guarantee the actual sale will be exactly just that number. And because of that, actually, we, instead of providing a point predict, like 8.44, we provide prediction interval. Very similar to confidence interval, we provide a range and say, you know what, the predicted quantity of milk sold will be within that range. Now, before we move to the prediction interval, I also want to mention this cautious note there. It is dangerous, though, for us to predict outside the range of the X variable, okay? You're using data to estimate the model. Then for your prediction, we will be very careful if we have to predict outside the range of the X variable. So I want to move back to our data quickly and show you what I mean. So back here, this is the data we use to estimate the model, right? So if you focus on the selling price, the range is between $1 and $2. That's the range. And therefore, when you predict or forecast the quantity of milk sold, you want to predict for prices between $1 and $2. And if you want to predict for $2.5, you want to be very careful because the result could be misleading, all right? So that's one cautious note about forecast using regression model. Okay, so let's look at the prediction interval. It is available in Minitab. So let's head over to Minitab and see how we can obtain the interval, then come back and continue our discussion. So here we go. That's the Minitab dataset we have. We want to do the prediction. So we need to go back to stat, regression, regression again, and this time we'll want to pick predict. And in Minitab, when you do this, when you do predict, Minitab will assume that you want to use the very last model you estimated, okay? And the response variable is still weekly sales. What we need to do is to specify the selling price. We need to tell Minitab what value of X we want to use for the prediction. It is $1.63, so we type in 1.63. And click on OK. There we go. We've got the prediction. The predicted selling quantity is 8.437 or 8.44, but what we like is really the confidence interval and the prediction interval reported. So let's go back to the PowerPoint slides and continue our discussion there. And you will notice that there are two intervals reported, a CI, confidence interval, and the PI, prediction interval. Why two? Well, they are different actually. The prediction interval will provide the interval predicted for 1 week only, okay? Because this is weekly sales of milk. If you want to predict for one particular week, you're gonna provide this interval. For the confidence interval, it's the prediction for sales for the average of multiple weeks. Okay, so if you say, I'm gonna predict the average sales for the next 5 weeks, then you want to provide the confidence interval, okay? Also, if you compare these two intervals, you would notice that the confidence interval ranges from 6 to 10, and the prediction interval ranges from 1 to 15. Apparently, the prediction interval is much wider than the confidence interval. We didn't mention this previously, but I want to ask you to think right now. For intervals, whether it's prediction interval or confidence interval, do we want it to be wider or narrower? Or in other words, would it be more useful to provide you with a narrow interval or a wider interval? And the answer should be narrower. If you picked on wider when I ask that question, I want you to think about the following. So you come to me and ask, well, can you provide me a range of the course grade that I'm going to receive for this course? Okay. And I can provide you with the widest interval ever, which is from 0 to 100. Apparently that is nothing, right? That's not useful at all. If instead I provide a narrow interval based on your performance so far, there's only one exam left maybe, and you have been performing very well, then I may say, well, the interval I can provide you is between 80% to 100%. So that's a minimum B. That is much better, right? So we always want narrow interval. But back to our prediction here. You might say, well then, let's always provide the confidence interval. No, it doesn't work that way. The confidence interval is narrower just because when we predict for multiple weeks, and when we calculate the average of these multiple weeks, we can smooth out the random errors. We can smooth out behaviors like me going into the store just buying 2 gallons instead of 1 gallon out of no reason. Okay, there are people like me who are buying more for no reason this week. There might be people who are buying less for next week for no reason. And when you average these weeks, you are averaging out the randomness. And therefore, we can provide a narrow interval for the confidence interval. So that's the end of our discussion for this linear regression. Next topic is we want to do some variable transformations. That is, if we find out X and Y are not particularly following a straight line relationship, instead of going to rely on a quadratic trend or an exponential curve, we can actually sometimes transform the variable to make it a straight line relationship. So to make it linear, there are several potential options out there listed. You can take the reverse of X, you can take log of X, you can take square root of X, or you can take X squared, okay? And actually log of X is used quite often. So let's take a look at an example. Gilbert Garcia owns a chain of hardware stores in Chicago, Illinois. He is interested in predicting his monthly sales using knowledge of the corresponding monthly advertising expenditure. Gil selected a random sample of 40 months of data from company records. So let's take a look at the graph on the left-hand side. This is not our formal regression analysis, but if we want to just visually examine whether a straight line regression would work for our data or not, we can do something called fitted line plot. And I'm going to show you how to get this in Minitab later. As of right now, let's just take the result and discuss. What I see here is that based on the blue dots, I don't see this regression line, which is the red line, is a good fit for the data, right? It's apparently a curve that looks like something like that. So it seems like the quadratic curve might work better, right? We could do a quadratic trend for the data. But the other option we want to talk today is to do a transformation of the data. What if we transform the x variable? So before then, let's further confirm that the straight line is not a good fit, although visually we can already examine that. But this is a very good example to show you when we check the residual will tell us the problem. So here's the residue we've got for the regression line for our data if we decide to fit that straight line. And the residual shows very clear pattern here. When the fitted value is small, the residuals are small, and then residuals are increasing as y increase. Then after the peak point, the residuals started to decline as the fitted variable continued to increase. Okay, and we can also see the pattern is that for small y values and large y values, the residuals are negative, and for values in the middle, residuals are positive. That's definitely some pattern we want to further investigate. So therefore, let's consider the 4 different transformations of x. We've got log of x, square root of x, x squared, and 1 over x. Then for each of the transformation, we will get the scatter plot to compare and determine which transformation give us the best result. For this simple example, clearly, the last transformation give us the best result, which is 1 over x. So that will be the one we will go with for our further analysis. Therefore, right now, I would like to move to Minitab and show you how we get the fitted line plot as well as the transformation, and then we will carry out the regression analysis formally. So here's the data set. The name of the file is hardware store. And let's do the fitted line plot first. We go to stat, regression, and pick fitted line plot. So the response variable y will be sales, and the predictor x will be expenditures. For the fitted line plot, we can choose among linear, quadratic, and cubic. We will stay with linear since that's what we first discussed. And if for other situations you want to visually examine whether quadratic is better or not, you can just pick quadratic and look at the results. So let's do linear for now and click OK. Then there we go. We've got the fitted line plot that we saw earlier. The next thing I want to show is how to get the transformation of x variables. We decided 4 of them, so they are x squared, log x, square root of x, and finally 1 over x. In order to get the transformations of x, we need to first define these variables within Minitab. And that's why I typed the name or the label for those 4. Then we go to Calc. Under this tab, you will see all different kinds of calculations. The one we want to use is the calculator. So we need to first define where we want to store this new variable. Let's do the first one, x squared now. So you want to double click on x squared. It will be filled in the box. For the expression, we want expenditure times expenditure. So we do double click on expenditure. Multiplication is right here, so click on it. And then double click on expenditure again. So this means x times x. And then click OK. We've got the number. Next, let's do log of x. So we go to Calc, calculator, and this time double click on log of x. There we go. For the expression, it is highlighted automatically. You can either use backspace to delete it totally, or you can just leave it like that. Don't touch it. Don't touch anything up there. What you want to do is for log x, we can't define it ourselves, so we rely on the function. the list of out functions are here. And we will look for log of x. There are two log of transformations. One is the log with base 10, okay? And the other one is the natural log. So start with n, that's the natural log. For this particular example, we're gonna do natural log, and really it doesn't matter that much, even if you did the base 10 log, it's just different scales. The results will be the same in terms of the shape of the scatter plot. So the reason I chose natural log is really because the numbers are relatively small. If we are looking at large numbers like thousands, millions, then the base 10 log will work better than this natural log. All right, so I'm gonna click on expenditure, because for the log, you need to specify what values you want to take the log. So double click on expenditure and click OK. And there we got the logs. For the square root of x, similarly, we'll go to calculator. And we want to store that in square root of x. Now this time log of expenditure is highlighted automatically. We still need to rely on the function to get the square root of that. So we will go to start with s. There we go. That's the square root. So I'm gonna double click on it, or you can click on it and say select. Either way works. And within expenditure, whatever left was there is highlighted. So now I'm gonna double click on expenditures to get the right expression. Now we're having square root of expenditures. So click OK again, and you will see the numbers are filled in automatically. Lastly, we will do 1 over x. So that is calculator. Double click on 1 over x. And this time we can define the expression ourselves. So you want to type 1 divide by expenditures. That will give us the value of x. So click on OK, and there we go. Right? So next step is to obtain the scatter plot for each pair and then see which one gives us the best result. I will just do one to illustrate how to do it. Actually, we learned how to get the scatter plot before, but just as a review, you will go to graph, scatter plot, click it, and click it OK. So the y variable is sales, and the x variable for the first one, we want to do x squared. Then click OK. And then we will get the scatter plot for the first transformation. So we don't see much improvement. It still shows a curve, which means not good idea. So as we discussed earlier, we decided eventually we're gonna use 1 over x as the transformation. And therefore, let's carry out the regression analysis formally. We'll go to stat, regression again, and do fit regression model. The response variable is sales. The predictor x variable will be 1 over x. That's the new x we want to use. And if you've chosen the residual plots before, the second time you run the model, it will still be there. So we have 4 in 1 as the residual. That's something we want to look at later. So click on OK. And we've got the regression results together with the residual plots. So now let's return back to our PowerPoint and continue our discussion. So here you see the same results from Minitab. Let's go through the results in more details and see what we can find. First of all, here's the regression equation. Okay, sales is equal to 4.28 minus 12.7 times 1 over x. And notice that this slope coefficient is negative. Doesn't make sense. We need to ask. We are looking at the relationship between sales and the reverse of expenditure, advertising expenditure. Now, if it's expenditure itself, we would expect sales and advertising expenditure to be positively related. But if you are taking 1 over x, then you should expect a negative relationship, which is what we got. So that is the right thing. Now, next, if you look at the table for the coefficient, we'll see the same coefficients listed here. We will also notice that the p-value for the t-test is virtually 0. So that means we have good news because we want p-value to be less than 0.05 so that we can reject the null hypothesis. And we do for this slope coefficient. And therefore, now we can say sales and 1 over x, or we can easily say sales and expenditure are significantly related. So the next criteria we want to look at is the R-square in the next table. Turns out to be 98.11%. Really good R-square, meaning that our linear regression model fit the data very well. And actually, if you look at this scatter plot, you can see that the observations almost form into a straight line, which tells us we will have good results. All right. And lastly, let's examine the residual plots to see if any assumptions are violated. Let's look at the first two on the left side. Both of them will allow us to determine if the data follows normal distribution. And the answer is yes to me, because if you look at the normal probability plot, except for this observation right there, the rest of them are pretty much very close to the red line, which means normal, the assumption of normality is not violated. In addition, the histogram also shows a rough bell-shaped curve. And therefore, I don't see anything suspicious. Next, we want to examine for the constant variance or homoscedasticity. To me, I don't see anything suspicious either. I do see the variance to be constant. It's around this range, except for one troublemaker. However, we don't usually make a conclusion based on just one observation. So we are not very strict with this in the sense that in this situation, we don't say heteroscedasticity is violated. Lastly, if you look at the residual plot, we expect it to be random, no pattern, which is the case in the last graph. At least to me, I don't see anything suspicious or any systematic pattern, but in comparison, when we fit the straight line, we see a very strong systematic pattern. Therefore, we will say for this model using the transformed X, the residuals are randomly distributed. All right, so that's pretty much all we have for regression analysis. As a final note, I want to give you a couple of more examples about regression used in practice, because regressions are used in practice a lot, and they are useful tools for conducting analysis and making business decisions. And the first one is about product consumption. Let's say a manufacturer is trying to forecast beer consumption per week by looking at demographic information and other related variables. The manufacturer could look at income, age, education, and other demographic information of the surrounding residents to determine the consumption per week so that the manufacturer can better plan for the production and better predict for the sales within that area. It could also be the analysis of sales. A retailer may want to forecast the sales of a product, especially if you want to compare price differentials. If you want to say, well, what if I set two prices and I want to know the effect of changing prices? You may consider setting different prices in different stores and see what happens as to the sales. And of course, you want to set the two stores far away, otherwise people can drive to the other store wherever they find cheaper price, right? But if you put it into two different stores that's far away and with two different prices, you could effectively capture the effect of price differential on the sales. However, you also want to control for income of the community, the store staff, because that sometimes matters, and also maybe competitors as well as other factors. And when I say control for, what I mean really is to also include these factors in your analysis. And this actually relies on what we will learn in the next chapter, multiple linear regression, where we will include all of these variables in the regression. And then we will be able to say, well, what if we have the same income, the same alert store staff, and the same number of competitors? Then we compare the effect of price differential on the sales of the product. And finally, it could be a situation where we have a new issue of stock and someone needs to determine the pricing. What will be the appropriate price? And we know that depends on a couple of factors, including the regional economy, the income, population, visibility of the firm, among others. Then what we could do is to run regression, use data on other similar companies with who also issued stock, then derive an appropriate price for this new issue. So all of these will involve the use of regression. Of course, they will all involve a more realistic one, which is the multiple linear regression model that we will discuss in the next chapter. All right, so that's all we have for chapter 6. And let me know if you have any questions.